Hello and welcome to lesson number 3 in Unit 5 Sine Functions in our grade 11 University College math class. So today we're going to tackle the first of our sketching of sine functions. In order to anchor that to something we've been doing, we're going to start back with the unit circle that we looked at in lesson number 2. So let's zoom in on our unit circle. Again, the idea behind the unit circle is that you've got these inscribed triangles that are built sort of on the inside of this circle that has a radius of 1. That's a unit circle. But what we're considering today is that imagine this wasn't a unit circle. Imagine it was a circle with radius whatever. We'll call it r for now, but you could put any value in there other than 1. Let's see how that would go about impacting the way that we find the sine ratio from these inscribed triangles. So let's start by picking our reference angle. We'll just call it angle theta there. And from our reference angle, this is our adjacent side here, our opposite side here, and our hypotenuse over here. So the sine function, or rather the sine ratio that we would take from this inscribed triangle, and any inscribed triangle in this, no longer a unit circle, but still a circle, it would be the sine of angle theta is equal to the opposite over the hypotenuse. And now using the letters provided for us, that would be sine of angle theta is equal to y over r. Now last time, as I said, we were dealing with a unit circle, so r became 1, so y just became equal to sine of theta. However, this time, let's try to isolate y, and we'll keep r in the mix, because it may not be 1 in every inscribed, or in every circle that we deal with. So let's put our sine theta over 1, and we'll cross multiply, and what we end up with is r times sine theta equals y, or written a slightly different way, y equals r times sine theta. So this reorganization to isolate y has given us a sine function with an r value out front. And this, as you remember, r is the radius of our circle, the distance from this center point to anywhere along their circumference, and that can happen sort of anywhere that we want along here. However, the point I think is maybe the most interesting out of all these, and I'll just sort of erase this stuff, is the highest and lowest point. These will also have a height of r, whatever the radius of our circle happens to be. I think that's important, because if you could imagine sort of taking this shape and spreading it out sort of in this direction, it's starting to look a little bit more like this sine function, and the radius of our circle is starting to look a lot more like the amplitude that we were looking at in the last lesson. So what I'd like you to do now, as a way of sort of illustrating this next point, is to complete this table. Now, I'm not going to waste your time by just sitting here on my calculator and typing in all of these values, but what this is meant to do is to help you develop a sense of how that r value out front, which you'll see here in these 3 examples, is 2, -1, and 0.5 respectively. By working through these tables and typing in, for example, 2 times sine of 0 degrees, 2 times sine of 30 degrees, etc., it's meant to help you see how the a value, which is the spot where we currently have put the variable r, how that impacts the way that our sine function looks. So, as I said, I'm not going to copy it all out. Or rather, I'm not going to do it with you. You can do this on your own. You're welcome to copy mine down. You're also welcome to do it through your calculator. That's fine. And then what we're going to do is plot those points on our graph. Now, we only need to do the first full rotation, the first full period. So now would be a great time to hit pause, fill in all this information, and when we come back, we'll talk a little bit about what we've found. So do that now. And you are back. So when we completed these tables, there are a few points that I'd like to point out that are common. For example, they all still have 0 at 0 degrees of input. They all still have 0 at 180 degrees, and they all still have 0 at 360 degrees, which is that full cycle. And you can see that illustrated here, here, and here on our actual graphs, it still hits, this sine function still hits our equilibrium axis 3 times, once at the beginning, once in the middle, and once at the end. The thing we notice changing is our high point. Now this was our original function, our y equals sine x, and then we had y equals 2x, and we'll notice that it goes up to a high point of 2. The negative sine x goes down to -1 as opposed to going up to -1. And the 0.5 goes to a high point of 0.5. And you'll see those same values mirrored over here. The regular one, the y equals sine of x goes down 1. The y equals 2 sine x goes down 2. The y equals negative sine x goes only, in this case, up 1. And the y equals 0.5 sine x goes down 0.5. So what we're seeing is differences in the highest and lowest points. And if we focus on those sections of the table, what I hope we're going to realize is that when we have an a value of 2, the highest and lowest points are also 2, positive and negative, of course. And that when your a value is 0.5, your highest and lowest points are 0.5. And when you have a negative a value, so in this case it was -1, we still go to a maximum and minimum of 1. It's just their order is sort of reversed, and I guess that's what you would call a reflection across the equilibrium axis. There's just sort of a switch of when it happens. And again, visually you can see that normally our sine function goes up to a high point and then down to a low point, and the reflected one, which is this guy here, it goes down to a low point before going up to a high point. So that's how your a value impacts the shape of your sine function. It impacts the highest and lowest points and whether or not there's a reflection across the equilibrium axis. So let's do some range now for our functions that we've graphed. I'll just sort of tidy them up. Oh gosh, that's a lot of, I need to keep that. Okay, so we're going to leave all of my mess on there. It'll be easier than trying to clean it up, I think. So let's look first at the range of our y equals sine, 2 sine x. So that's the orange one there. It goes up to a high point of 2, and it goes to a low point of -2. So as we articulate that, our range then would be the set of all y, such that y is an element of real numbers. Our low point is -2. There's our y. Our high point is 2. So y will be less than or equal to 2, and -2 less than or equal to y. So that's our range of f at x equals 2 sine x. Let's look at f at x equals negative sine x. That is the one that I've put this highlighter on. Let me see if I can get it off there. Yes, I did. So that's the green one. So again, what is our lowest point that we're hitting here? -1, high point 1. So despite the fact they occurred in a different order, they're still it's still the same maximum point, still 1, and the minimum point still the same, -1. They just happened in the reverse order. Totally fine. Doesn't change the highest and lowest points. So then our range would be the set of all y, such that y is an element of real numbers. We've got -1, y, and 1 is our high point. So y is less than or equal to 1, and -1 is less than or equal to y. And now to 0.5, that is the purpley sort of one we put on here. So our high point is 0.5, our low point, -0.5. So those are our two optimum values. So let's get this on here. So the set of all y, such that y is an element of real numbers, where we have -0.5, y, 0.5. That will be y less than or equal to 0.5, and -0.5 less than or equal to y. So those are our ranges. Again, want to make sure that you're seeing these patterns. The high and low values are the same max and min points that you're seeing in the graph. 2 and -2, 1 and -1, and 0.5 and -0.5. So those are the values that are reflected in our range, which is helpful for us to remember. Here we have a summary. And the summary just articulates exactly what we just said, which is that a negative a value, and again the a value, maybe I'll just write this out quickly here. So the sine function that we look at generally, the basic one, is y equals a, whoops, stop it, y equals a sine bracket x minus d plus c. So that's sort of the form of the sine function that we're going to be looking at. Today we're looking at what a does. So a does a couple things. The first is if our a value is negative, it tells us that we are going to have a reflection, a vertical reflection across, and that should not say the x-axis, that should definitely say the equilibrium axis. So equilibrium axis. A -1. So essentially what that means is that instead of our sine function going up first and then down, it's going to go down first and then up. And then we're looking at expansions and compressions. So where our a value is larger than 1, we call that a vertical expansion. And essentially what that does is it amplifies our highest point up to an a value. In a lot of ways, the a value is synonymous with our amplitude, the distance from our equilibrium axis to our highest and lowest points. Now, if a is between 0 and 1, so a proper fraction, we would call that vertically compressed. And again, that's going to impact the height of our highest and lowest points, our max and min values, when we're looking at a sine function and how it's graphed. So we're going to stop here. When we come back, we're going to do 2 sketches. And as I've said, I think in lesson 2, sketching is kind of one of is maybe the biggest and most complicated idea that we're going to tackle in Unit 5. So that'll be the thing that we're going to start to look at in part 2 of this video and in lesson number 4 as well. So we'll see you in part 2 for some sketching.